We're looking at similar and special right triangles. All right, but we are looking at these similar and special right triangles. We're kind of two topics rolled into one today. So let's just see what we know so far. Oh yeah, geometric mean. Remember that thing?
Yeah, it was fun.
It is fun. So if you've got two numbers A and B, and I want its geometric mean x, how do I find x?
It's undo his mindless calculator plug-in.
What's the formula? If I have A and B, how do I find geometric mean, Amanda?
Okay, x equals rad A times rad B.
Perfect. And I just combined them. You're correct as well. She said it's this, which is equivalent, right? So it's the same thing, either one. Great, so we need to know that. So if I want to find the geometric mean of 9 and 16, we would say x equal, you can do it two ways. You can do it this way, or I like the way Amanda said it, when they're both perfect squares, this way is a little bit easier, right? You get your 3 times your 4, you get 12. Or you can just multiply this out, you get 144, and you get 12. Either way, you're going to get to the same place. So that's our quick review of geometric mean. Now let's remember altitude. Altitude, altitude, altitude. It measures the what of a triangle, Joseph? What does it measure, altitude? Height. Height and altitude. How high is the triangle drop in altitude? And you drive from a vertex to the side opposite the vertex, which is kind of like dropping in here, and it's blank to the side it touches. What word am I looking for there? Definitely perpendicular. Oops. So that first little paragraph there, is the second bullet there, measures the height of a triangle and is perpendicular to that opposite side that it touches. Yeah, review, we know this. I hope. Okay, so here comes a theorem. Get ready for this now. So look what I got here. I have a right triangle, and from the right angle, I dropped an altitude, a perpendicular line to the side opposite. So if you do that, if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So you see there are three triangles here, small, medium, and large, and they are all similar to each other. They're not going to illustrations somewhere. Let's see if I can find it. Yeah. It's kind of a little hard to see sometimes how they come apart. So I'm dropping an altitude. Let's see. Here's one of them, right? Flying out. Here's one triangle. Here's another one. This one is maybe the easiest one to see. Now watch what happens to the big one. It's kind of turning around. It's rotating. And now I am flipping it over. And that's where the similarities are. So when you have to match sides, remember how similarity works? The corresponding sides have to match this to this to this. And this one to this one to this one. And maybe the hypotenuses are the easiest ones to see. So wow, look what's going on in there. These three triangles, you kind of have to have real good visualization skills. They're probably better than mine are, the ones that need to have to do this. So we have three triangles. We have this little one, which I'm calling triangle 1. We have this medium-sized one, which I'm calling triangle 2. And then we have this big one, which I kind of have to turn around a bit to get triangle ABC, which is similar to the others. So ABC is similar to CBD, and it's also similar to that one, and these two are similar. All similar triangles. All right? Okay. And because they're similar, we can establish some relationships. So again, I'm keeping my pulled apart triangles where I can see them, because I think it's difficult to see when they're all packed up together. So let's see, if I'm looking at 1 and 2, and I'm trying to match my corresponding sides, right? So BD over CD equals CD to AB, correct? Right? I'm getting this proportion. If I look at 3 and I look at 1, and I'm comparing hypotenuses and shorter legs, so let's see. AB, that hypotenuse goes to that hypotenuse, and this shorter leg, CD, goes to BD or DD. So those are a match. And then triangle 302, I'm doing hypotenuses and longer legs. So AC, or A, go this way, AB to AC is the same as AC to AD, right? They're all going to have the same scale factors. They are all similar. Okay, fantastic. Now I'm looking. Notice, okay, CD, which is the altitude of ABC. Here it is. Here's ABC, and here's CD. See how it's its altitude? It's the geometric mean of BD and AD. What? Let's go up here. So if I do my cross products, I get CD times CD, that's CD squared, equals AD times BD. If I take the square root of both sides, I'm getting a geometric mean of AD and BD. I'm multiplying and I'm taking the square root. So this thing here, CD, is the geometric mean of AD and BD. CD, geometric mean of those two pieces. Alrighty. CD, which is, yes? They're the same CD. It's the same CD. This is why this is so like, what? It's a really confusing kind of a picture. Alright, let's stay with me here. CB, if I'm looking at the big triangle here, CB, it is a leg of ABC. It's the geometric mean of AB and DB. And now I'm looking at the second thing. What's happening here? This times this, CB squared equals that times that. I'm going to do myself lost here. AB times DB times DB. So CB equals the square root of AB times DB. Geometric mean. So where's CB? It's the geometric mean of AB, this whole big piece, and DB, this little piece. And let's see what's going on with here. AC, which is this leg of this triangle, it's the geometric mean, I'm saying, of AB and AD. Why? Because I've got this proportion. AC squared equals AB times AD, which means AC is the square root of that. That's a geometric mean. Square root is a number. So what is that one now? AC is the geometric mean of this whole thing and this segment. What? Alright? Semi with me? Tiny bit with me. Geez, I'm with you. Alrighty. So, the thing with this is, you can find missing sides based on these proportions. So if you can kind of, in your mind, visualize how these triangles break out and what matches, you can set a proportion. I know when I look at this, I get mighty confused and say, well, which one does that go with? I think BB goes with that one. It gets very, very, very confusing. Using geometric mean helps us. So I've got these theorems here. I've got the geometric mean altitude theorem, which is what we just showed. That CD, if you have an altitude, this CD, it's the geometric mean of AD and DB. This equals this times this, take the square root. We also have a leg theorem with the geometric mean. It says, and there's a whole bunch of words here, let me make that a little easier. If you look at the leg, it's going to be the geometric mean, now watch carefully, okay, of the segment closest to the leg you're interested in, times whole thing, take square root. Geometric mean of this thing and whole thing. If you want the other leg, it's the geometric mean of the segment closest to that leg you're interested in and that whole piece. Best way to see this is through an example. Yeah.
How do you know which is closest to the AC is touching CD
Right.
and AD?
If I'm looking, I'm going to call this one S. CB, it's the one that it touches. This is the one that's closest, this one. It's always going to be this opposite side that I'm interested in. Right? So it's this side, and we're always looking at the bottom. So it's this piece times whole thing, take square root. Let's do an example, and hopefully there's an adult coming up here. All right, find the values of the variables variables. I think this is the bottom of the page here, bottom of page 1. All right, so let's see what we're talking about. It's harder to say than to do. okay? So first you recognize, okay, it's a right triangle, I dropped an altitude from that right angle. So I want the altitude. So it is the geometric mean of this piece and this piece. So the geometric mean of 15 and 10. How do you find geometric mean? You take the square root and you multiply those numbers. So that's the square root of 150, which is the answer, but we always put it in simplest radical form. What is that? I know I've got 25 going there, right? 6 times? 25 times 6 will be 150. So this is 5 radical 6. Okay, let me say it, I'll say it again. So what you do is, if you want the altitude, it is the geometric mean of the two segments that the altitude creates. These two segments. Yes? Yes. Right triangles where you're dropping that perpendicular from the right angle. This is the only thing. What I'm doing is those are proportions. You can set up proportions too. And I'll probably mess it up because I always do. So let's see, 10 and x, I think they go together. Right? This side to that side is the same as this side to that side, x to 15. So that means that x squared equals 150. So x is square root 150. We're back where we started. So you can do this using proportions. You can. I personally find it hard. I'm trying to find who matches what. It's really hard to see when they're all bunched up like this. So I can see, oh, I'm just going to be taking the geometric mean of these 6 times. It's going to work every single time. Use what's easier for you. I find this easier once you've done it a couple of times. All right. Looking at this example now I want to find a leg. So a leg theorem says if you want a leg, it's the geometric mean of the segment closest and whole thing. So if I want this one, and I'm upside down a little bit, so I'm dropping over here, it's this thing and this thing. That's what I want the geometric mean. The segment closest times the whole thing, I think that's 26, geometric mean, right? Multiply the numbers, take square root. Are we okay with just this part? The rest of it is computation. Okay?
No, how are you sure that it's not xy? Because xy is close to wx and wg.
What? How do I know it's what? XY?
Xy and wz are both equally close to wx because they're both touching it.
I'm looking at the hypotenuse of the big triangle. I'm always looking there. Yeah, always look at the hypotenuse of the big thing. And it's the piece that touches the segment you're interested in. And both things. 8 times 26, I got 208, is that right? Okay, and then I have to find the perfect square that goes into it. It's actually 16 times 13. I believe, if I did it right. So this became 4 radical 13. Moving so far. Because here comes a harder one. Oh. Okay. Now I'm trying to find this. Now, the geometric mean theorem says, I'm going to call this little piece x and this little piece y. The geometric mean theorem says you take the geometric mean of x and y. I don't know either of them. Like, what? So we can try and find them. Or we can use the proportions. So, let's see, what do I know here? I can confuse myself how to do this. I think y is this one's long side, and so that one's long side I think is 8, and then I think that's 6. No, I don't even think I'm doing it right. I get very, very confused. I can't do them this way. So I'm not doing it. I can't even figure it out. Okay, let me look and see. This is the short side, and this is like a long side, and that's the hypotenuse of this one. And then this one, I think I have to move this whole thing or something. I don't know. I'm lost already. I'm lost already. So, yes, absolutely. I'm not going to do it that way. I really have trouble with it. So what I do is I say, wait. Look at this big triangle. I know 2 of the sides, don't I? Don't I know 2 of the sides? How do you find the third side? Pythagorean theorem. And it's 6 and it's 8. So if I divide by 2, that's a 3. If I divide front 2, that's a 4. 3, 4, 5 times 2. So this whole piece is 10. Okay, that whole piece is 10. Now, I know this one's 6, right? And I know how you find the leg. It's the geometric mean of this piece and whole thing,
You
right?
don't know that piece.
I know whole thing, though. I'm only missing one thing. 6 is the geometric mean of this piece and the whole thing. Right? Isn't it? What? Oh yeah, I'm going to square both sides. I want to get rid of the square root. Square both sides.
Then you go back like 2 steps.
Okay, what I'm doing is I'm using this theorem. This one is the geometric mean of this is y, and this whole thing is z.
Yeah, I got that.
X is the geometric mean, whoops, of y, z. So I'm going here. I know x, and it's the geometric mean of this piece and whole thing. So 6 is the geometric mean of x and 10. That's where this is coming from. You get there. Square both sides because I don't want a square root here. That's how I get rid of it. And then I divide by 10. And x is 3.6. If the whole thing is 10 and this piece is 3.6, what's the other piece?
Oh,
It's 10 minus 3.6, right? Yeah, 6.4. Now I have two pieces. So y is the geometric mean of this and this. So I'm going to multiply those two things and take square root. What? Wait, who got there with me? Who made it? Anybody? We're just writing it down.
I'm using Pythagorean theorem to solve for y.
You can do that, right? See how this is 3.6 and this is 6? This squared plus that squared is that squared. You can totally do that as well. Let's see if we get the same thing. We want this altitude. We'll keep getting back to what's this length. And she said, well, you found this piece. Here's the right triangle. Go ahead. Yeah, Pythagorean theorem. You can. So let's see. Let's see if we get the same thing. 3.6 times, I don't know. I put this in my calculator. I don't know what 3.6 is. 3.6 times 6.4. 23.04. And then I took square root. I got approximately, or maybe even exactly 4.8. Let's see what we get. Take the square root and whatever it is going to 4.8. Is that what you got? If you did the Pythagorean theorem, is that what you got?
4.8, I'm not going yet.
Mm-hmm.
Wait a second, I thought, you were supposed to read 12.96, like, years, like, very
No, this all worked out kind of nice. Without rounding, I got kind of nice little
I don't
decimal
think
numbers.
that's
So that's kind of all I have to say about that. Now, if you can rip apart these triangles and see them better with the proportions, by all means, go ahead and do that. I don't know, I just like a mental block for me. I had a lot of trouble with it. Okay, special right triangles. Okay, it's a different topic. Special right triangles. There are certain triangles we kind of have to know how they work. So we're going to use the Pythagorean theorem here. This, I don't believe is on your paper. We're just going to look up here. We're going to find missing sides, right? Pythagorean theorem. I've got a 5, I've got a 5, I've got an x, right? This is my hypotenuse. So 5 squared plus 5 squared is x squared, right? So if I want x, I want the square root of 25 plus 25. That's 50, right? And that is going to be 25 times 2, right? So 5 radical 2? So this x is 5 radical 2. Okay, this one, okay, we've got a radical in here. That's my c, right? So x squared plus 3 squared is that whole thing squared. So that means that x squared equals the square root of this thing squared, which is what? 9 times 2 minus 3 squared, which is 9, which is 3. All right. Let's see what's going on here. This is my c. And so now so it's x squared plus this whole thing squared equals 12 squared. So x squared plus, let's see, that's 36 times 2. 72 equals 144. Now I gotta subtract that 72 from 144. No, so it's 2 and 72? I think so. So x is that square root of 72. Oh, reduce that radical. 72 is 36 times 2, right?
I have a question.
Hang on 1 second. So there's 6 radical 2, 6 radical 2. Hang on. All right, so let me get rid of some of this computation. It's a little hard to see. I just want to get rid of this so we can see what we found. And so you're already noticing that, listen, it's 45 and 45. All of these are 90 degrees right triangles, except that they're 45, 45. They're isosceles. So these have to be congruent sides, right? And they are. So that's good. It's working, right? The math is working. They're supposed to be congruent, and they are. Excellent. What else are we maybe kind of noticing here, if anything? 5, 5, 5 radical 2. 3, 3, 3 radical 2. 6 radical 2, 6 radical 2, 12. Yeah?
I guess hypotenuse is kind of like, it's a little longer than the length of the leg.
Okay, it's a little bit longer.
Not longer.
How much more? How are we getting that hypotenuse? Oh, but just a little longer, yeah? What do you mean it's square root 2 longer? Am I adding square root 2? Well, what does it mean, 5 radical 2? Is that 5 plus radical 2? Multiply. Multiplying by radical 2. Is that true here too? Well, let's see. Is 6 radical 2 times radical 2? Did I get 12? Well, radical 2 times radical 2, 2 times 6. Oh, we are. So it's the side times the square root of 2. So the hypotenuse apparently is, let me get rid of some of this mess, the leg times the square root of 2. So what would the hypotenuse be in an isosceles right triangle where the leg is 1? So I've got this picture here. The leg is 1, the leg is 1, 1 times the square root of 2, square root of 2. So you take the leg, you multiply the square root of 2, you can get a side. Now what if, like this one, I know the hypotenuse, but maybe I don't know either side, right? This one I'm kind of giving a little hint. Then how can you, if given the hypotenuse, how do you find the side? Divide, right? So if I multiply the side to get side by radical 2, then I would divide the hypotenuse. Because 3 radical 2, right? Divide by radical 2 is equal to 3. So if you have a side, multiply by square root 2, you get a hypotenuse. If you have a hypotenuse, divide by that square root 2, and you have a side. And that is the 45, 45, 90 special triangle. So here's the theorem. In a 45, 45, 90 triangle, an isosceles right triangle, the hypotenuse is square root 2 times as long as each leg. Hypotenuse is a leg times the square root of 2. Now, as long, if you want to solve for the leg, divide both sides by the square root of 2, and that's where this came from. Leg is hypotenuse over square root of 2. So this is the picture that is on there. So if you have a side of length A in a 45, 45, 90, the hypotenuse is a square root 2. So now I've got that picture. So it says use the Pythagorean theorem to generalize. Let's make sure we agree. A squared plus a squared, right? Does that equal this thing squared? Well, a squared plus a squared is 2a squared, right? What's going on here? There's an a squared. Square root 2 times square root 2 is 2. And I can write this as the same thing just by using commutative property. It works. Okay? So we just have to remember now, if you have a 45, 45, 90 triangle, any isosceles right triangle, the side times the square root of 2 will give you the hypotenuse. Hypotenuse divided by square root 2 gives you the side. So that's our first special triangle. Our second special right triangle is the 30, 60, 90. You have a 90-degree triangle, right triangle, and the sides are, the other angles are 60 and 30. So if you have that, let's see what we can figure out. So we're going to use the Pythagorean theorem once again. So this squared plus this squared is that squared. 5 squared plus this whole thing, 5 radical squared, is going to be x squared. So that's 25 plus, let's see, that's a 25, and that's a 3. 25 times 3, that's 75, equals x squared. So 100 equals x squared. So x is 10. All right. Let's look at this guy now. So this one's going to be x squared plus 4 radical 3 squared equals 8 squared. So x squared plus, right, 4 squared, right, is 16 times 3. 48 equals 64. So that means that x squared equals whatever 64 minus 48 is. Well, that's 14 minus 8 is 60. So x is going to be 4. And let's see what we got going here. X squared plus 6 squared is 12 squared. X squared plus 36 is 144. Oh, okay, x squared equals 144 minus 36. Alright, and 10. What are we?
Yeah.
I'm doing it wrong. 144 minus 36. Where's that calculator? Just do it. 144 minus 36. That's 14 minus 6. That's 13 minus 108, right? Okay, so x is the square root of 108. Ah, how do we reduce this thing? Do I have to put a square factor in there? I think we do. I'm pretty sure, I think it's this. 36 times 3 is 108. So this is really 6 radical 3. And again, let me just erase some of the calculated stuff. So I can just look at what we got and see if we do have some kind of pattern with this one. I think this one might be a little bit harder to see than the other one, but you might notice some stuff. Alright, so let's look at it and see if we notice any sort of pattern. 5, 5 radical 10, 4, 4 radical 8, 6, 6 radical 12. What do you see, Joseph? Nice and loud. I can hear you. Say it loud. I cannot hear you. The short side, I like how he said that. The short side, because this is 30 degrees, right, it's shorter than the side opposite to 60. The side opposite 30 appears to be half this hypotenuse. Side opposite 30 is half the hypotenuse. Okay, what about the side opposite to 60? Yeah? It's that short side times radical 3, short side times radical 3, short side. That's exactly what the rules are. So the hypotenuse is the shorter leg times 2, or you can say it's half the hypotenuse, and then the longer leg is the shorter leg times the square root of 3. Whoa. Okay? So let's see. I'm looking now at just like a simplified triangle here. What would the hypotenuse be in a 30, 60, 90 triangle with a shorter leg length of 1, meaning side opposite to 30? So you have to multiply by 2. And then what would the longer length be if this times radical 3? That's where that's coming from. Those are the rules. Wow, gotta keep those in. Oh, okay. So here's kind of more formally written, this was on your paper. In a 30, 60, 90 degree triangle, the hypotenuse is twice as long as the shorter leg, and square root 3 times as long as the shorter leg. Right. So if you know the shorter leg, multiply it times 2 to get the hypotenuse. And if you know the shorter leg, multiply by square root 3 to get the longer leg. It's the side opposite to 60. And the shorter leg is side opposite to 30. You can solve these for shorter leg, right? So divide by 2, divide by 2. If you want to find the shorter leg, take the hypotenuse over 2. You can also find the shorter leg by taking this longer leg and divide by radical 3. Here's a kind of a generalized look at it. So at right, we have an equilateral triangle. See, they're all 2A long, each side. Here's an altitude. Each side of the triangle measures 2A, find the altitude. So I think we've proven in a previous class that when you draw this, we get two congruent triangles, so therefore these are congruent. So each one of these is A. So I can use the Pythagorean theorem. This squared plus this squared is that squared. Let's make sure that's true. Let's see what I get here. Okay, let me make sure I'm setting it up right. So that's A squared plus that's an A squared, right? And that's a 3. So that comes out to 3A squared. Squaring this is 4A squared. And so 4A squared equals 4A squared. Okay. So let's see, what do we do with this? Oh. So the idea with this is now you're not going to sit there and use the Pythagorean theorem every time you see something like this. You're going to remember this, okay? We're not going to use the Pythagorean theorem. We're going to remember. So notice how this is an x and an x. So that means this is an isosceles triangle, which means that these angles are congruent, so they must be 45 degrees each. So I've got a 45, 45, 90 triangle. So if my hypotenuse is 9 radical 2 long, I have to kind of remember the rules. So with a 45, 45, 90, you take a side and you multiply by the square root of 2, right? And you get the hypotenuse. Or you can say a side is the hypotenuse divided by the square root of 2, and that's for 45, 45, 90. Right? That's the rule. So I have a hypotenuse, right? So if I want to find a side, I'm going to use this kind of a relationship. You take the hypotenuse and you divide by the square root of 2, and I get each side is 9. 9, 9, 9, that's it. Okay? Same note here, I'm also seeing that these sides are congruent, which means these angles are congruent. Which because it's a right triangle, they must both be 45. 45, 45, 90. If the side is 15 radical 2, how do I find the hypotenuse? You take the side and you multiply by square root 2. So take 15 square root 2, multiply by square root 2, 2, right? Grad 2 times grad 2 is 2, times 15, this must be 30. Okay? So those are two examples with 45, 45, 90. Now the rules with the 30, 60, 90 are a little bit more complex. So you take the shorter side and you multiply by 2 to get the hypotenuse. And you can take the shorter side and multiply by the square root of 3 to get the longer side. Okay? So I think those are our rules with those triangles, 30, 60, 90. Oh. So it looks like I have a shorter side. I know the shorter side. If I multiply it by 2, I will get the hypotenuse. So what is 7 rad 3 times 2? 14 rad 3. Okay, so that would be that one. Now, I want to get the 60. To get the longer side, it's the shorter side times radical 3. So I take my 7 rad 3 and I multiply by rad 3. Well, rad 3 times rad 3 is 3. Times 7 is 21. So there are my sides. 7 radical 3, 21, 14 radical 3. Wow. Let's see what's going on here. 30, 60, 90. I'm going to use these rules. Let's see, what do I know here? I know a longer side. Oh. So if I have a longer side, I should be able to find the shorter side by, let's divide by rad 3. The shorter side is the longer side over rad 3. So I'm going to take the longer side and divide by radical 3. Okay, this is an easy one, cancels out. So that's going to be a 5. And if I know the shorter side times 2 will give me my hypotenuse. So, do you have any questions so far here? Kind of just knowing these rules. Let's try the next one. I see a 60, I see a 90. I always do write in the other one. Maybe you can see that in your mind's eye that it's 30. I like writing down. I like seeing it. So I know here's the longer side, here's the shorter side, here's my hypotenuse. So again, they're giving me a longer side. So if I want to find the shorter side, the longer side over the square root of 3. So this must be a 3. And then shorter side times 2 gives me hypotenuse. And this may seem really hard right now. When you do this after a while, you do get very, very fast at it. You get quick. So we have to kind of slow it first to get something that's going to be really fast after that. Okay, what's going on here? 4, 4. Whole side is 4, right? So this is an equilateral triangle. I know all the angles are 60 degrees, right? But these get kind of bisected in equilateral triangles. So this 60-degree one is 2 30s. So these are actually two 30, 60, 90 triangles. We might kind of figure that part out. So let's see what I don't know. This H, if I look at just one of these triangles, is a longer side, right? So I know the shorter side and I know the hypotenuse, and it's working. Shorter side times 2 is the hypotenuse. To find the longer side, shorter side times square root 3. So this is going to be 2 square root 3. That H is 2 square root 3. Here, let's see it. Because it's the shorter side times the square root 3. Anybody with this too? Anybody just like, I just left. Oh, go on. No, are you with me?
Wait, it's like I don't see you.
She's on C, she's still working on it. And basically what we're doing now is we're doing the U-tries. It's problems. That's what that third page is. I do want to review with you this stuff. I think this part can be tricky. All right? So remember how this stuff works. If you have a right triangle and you drop one of these, if you want to find the altitude, it's the geometric mean of the two segments that are created, right? Altitude, geometric mean of those two things. A leg is a little bit harder. A leg is the geometric mean of the segment kind of closest to that leg and the whole thing. So this times this takes square root if you want to find that piece. And same on the other side. If you want this piece, this one, whole thing, take the geometric mean. So we've got another way for this one. You say, so you find the area, which is 1/2 base times height, which is 1/2 6 times 8, which came out to 24. Okay. This is 10. So 1/2 base times height, which is, or y, right? That's what we're trying to find, is also going to be 24, isn't it? So you said half of 10 is 5. 5y equals 24. So y equals 24 over 5, which is 4.8. Awesome. Fantastic. Love it. That's a great way to do it. I love when you guys find other ways. Putting up the answers that I got so that, first of all, they'll be on the recording if you want to watch these people look over this later. So I'm going to flip through relatively quickly just so that the answers are there for posterity, but also so that you can check your work, see how you're doing. One more page here, and then I can flip that. But if you don't finish now, we still have about 5, 7, 6, 7 minutes. So work as much as you can. But this is something I would really like you to keep working and see if you're doing it. If you're having trouble with some of them, maybe move on and come back to the other ones. But these are now on the recording if you want to see some answers. And I would like to go over some of them if you can. In this first one, 5 equals geometric mean, so I'll take the square root of what? The 3 times whole thing, which is x plus 3. Right? Whole thing. Yeah, that's the tricky bit with that. Square both sides, and I'm distributing at the same time. I'm just skipping stuff a little bit. So 3x plus 9, so what's that? 3x equals 16? So x is 16 over 3, which, that was about 5.3, right? So which is about 5.3. This one, I love the Joseph method. This method says, find the whole area. So area is 1/2 20 times 30, which is 300 square feet. Well, you can find the area the other way. It's 1/2 base times height. So the area is also 1/2 this base times that height. So 10 rad 13, that's over here, equals 600. X is going to be whatever 600 over ten rad 13 is, and I sure hope that comes out to 16.6. So you check that out, I hope it does. And this one, 6.9 equals the square root of 5x. If you square both sides for this one, what did I do up here? I think I got x to be approximately 9.5. I'll let you do that math to get there, square both sides. And then, that would be 9.5, right? They want a whole height, so you have to add, like, 14.5. These ones are just gonna have to get good at it. This is another 45 degrees here. 2 rad 2 multiplied sides by radical 2. 2 times rad 2 times rad 2 is 4. This one is also a 45, 45, 90. I know the hypotenuse divided by radical 2. 30, 60, 90. The side opposite the 30, the short side is 2 rad 3 multiplied by 2 to get the hypotenuse. Multiplied by rad 3. 2 rad 3 times rad 3 is 6. This guy, side opposite that is 8, so I got here, divide by rad 3. Remember how to do the rationalizing denominators? Remember this? So that's going to be your x. Multiply by 2 to get the y. So dividing by rad 3, remember to rationalize denominators. Whoa. I'm sorry I'm going so fast here, just because we're running out of time here. Oh, what do we do here? This is actually a 30, 60, 90. So the side opposite the 30 is half that. This must be 16 rad 3. Multiply the short side by rad 3. Car is turned off while the windshield wipers are moving. That's 60 degrees. So let's see, that means this little piece is 12, which means the side opposite the 60 is 12 rad 3. Really fast, but let's put it on there so you can kind of check